We're now going to discuss the absolute value function. And the absolute value function is a piecewise defined function that looks like this. So for positive x, it just gives back x, does nothing. And for negative x, it gives back minus x. In terms of the graph, this means that, well, for positive x, this is just y equals x. So it's this line here. And for negative x, it's y equals minus x, which is this line here. So notice here, for positive x, the absolute value function is just a straight line through the origin with slope 1. And for negative x, it's just a straight line through the origin with slope minus 1. In particular, for every x, this gives us a positive value. This is basically what makes it important to us. The absolute value function is of interest because it gives us a really practical way to talk about distances. So let's take a look at this. First of all, if I take the absolute value of 3, well, it just gives me 3. And if I take the absolute value of minus 3, well, what does this give me? So minus 3 is a negative number, so I get minus 3, so I get 3. So there we see that we get a positive answer no matter what we do. And now let's look on the real line here. What if I take 2 points here? Let's say I take 2 and 5. So what is the distance between 2 and 5? Is it 3? Is it minus 3? Well, so the thing is that when we talk about distances, we usually want to think of them as a positive number. So the distance between Lund and Malmö, 2 cities in Sweden, is it 20 kilometers? Is it minus 20 kilometers? Does it matter which city you say the first? No, it's 20 kilometers. So in terms of the absolute value, we can express this distance between these points as just the absolute value of their difference. And if I happen to take 2 first, I'll get the absolute value of minus 3, which is still 3. Or if I happen to take 5 first, I get the absolute value of 3, which is still 3. So in a sense, I can make a definition. So usually mathematicians don't make this definition explicitly at this level. We certainly do at higher levels, but let's do it now just for fun. So for AB in R, the distance between AB is given by the absolute value of their difference. And we don't care if A is bigger than B or not. This is always a positive thing. And usually, or when we look at this in higher courses, we can call this the distance function. So distance of AB, or we sometimes write just dist AB. And it's possible to define other distance functions than this. And in topology, you study the consequences of using different types of distance functions. And this kind of cements the type of intuition we can have about the absolute value function. Now, if the absolute value function is so interesting, then what properties does it have? Well, it has the following properties. Well, it has more than this, but these are like the fundamental ones. So if I take the absolute value of a product, then I get the product of the absolute values. Here, I'm just talking about real xy. So you can also do the absolute value of a complex number, but then it means you have to extend its meaning. So let's see, what else do we have? You can do the absolute value of a quotient. Of course, here y is assumed to be non-zero. And then you can do the absolute value of a sum. It doesn't look as nice, but well, it's quite nice. So this is a triangle inequality. And then I write a last rule here, which is very practical to have in a course in analysis. It's that if r is some number bigger than 0, then the absolute value of x is smaller than r, if and only if x is in the interval from minus r to r. I can write it like a double inequality here. And if it's closed here, or if it's less than or equal to here, I would put less than or equal to on both sides here. Now, a thing here is that this is just 2 statements about killing the sign. So this says that if I multiply x and y and then I make it positive, I will get the same result as if I made x positive first, y positive second, and then multiplied it together. Same for fractions. Here, these two are more, or should be thought more in the terms of distances. So here I take a number x and y, and then I wonder basically how far I've gotten from the origin. And I've gotten less far than if I first walk a distance x and then add a distance y. So you can, to understand this, you should really think about this in terms of lengths. And here also length. So maybe let's do this one a bit more explicitly. So here, let's scroll down. Here I can think of this in terms of the real axis. So this I can think of as the absolute value of x minus 0. So the absolute value of x I'm thinking here of as how far is x from the origin. Well, if x is less than or equal than r from the origin, what does this mean? Well, this means I can go a distance r here, and I can go a distance r here. Where do I end up? Well, here I end up at r, and here I end up at minus r. So if I go a distance less than or equal to r in either direction, I will end up in the interval between minus r and r. So that's the geometric intuition behind that statement. And similarly, you can make a drawing for this statement, which you absolutely should do, and is left as an exercise for the students in this course. But let's now do a proof. So, and we're going to do a proof for one of these two. And let's take 1. So proof for 1. And what's the proof technique? Well, if we go up here and look at the definition for the absolute value function, we see that it's a piecewise definition. So what he does depends on whether or not the thing instead of here is positive or negative. So this just screams for a proof by cases. So let's do a proof by cases. And proof by cases is a suitable strategy in to prove all 4 statements here. So what type of cases are we supposed to look at here? Well, we have here both x and y. So, well, let's look at the cases when x is positive, x is negative, y is positive, y is negative. Why not? So then case 1, 2, 3, 4. I'm not going to do all of the cases, but let's do a couple. So here, let's assume that x is positive, y is positive, x is positive, y is negative, and I can do strictly negative to keep the cases disjoint. Here now I take x strictly negative and y positive, and here x strictly negative and y strictly negative. So in each of these cases, I want to check that the left-hand side here is equal to the right-hand side. So we can make columns here. So left-hand side and right-hand side. So if both x and y are positive, then x times y is positive, meaning that this thing here is just this. If x and y are positive, then both of these things will be positive. So the absolute value function does nothing. So x in absolute value times y in absolute value becomes x times y. Left-hand side equal to right-hand side, and we're happy. What happens here? Well, if x is positive and y is negative, then the product will be negative. Well, if x is 0, then it'll be 0, the product. But in both cases, the result of this will be minus x times y. What about the right-hand side? Well, if x was positive, then the absolute value of x is just x, and if y is negative, I'm getting a minus sign here from the y. And together, I'm getting minus x times y, which is the same as the left-hand side. And again, I'm happy. And you can do the same thing here and the same thing here, and note that the left-hand side is equal to the right-hand side in each case. And this ends the proof, and we are done.